Dear students, Assalamu alaikum. In this lecture video, we are going to discuss 2D-NMR, that is two-dimensional nuclear magnetic resonance spectroscopy. For 2D-NMR, we have different type of techniques. For homonuclear 2D-NMR, it means that the protons are carbon. Means if we are going to study only proton NMR, or we can say that we are going to study the effect of proton on proton, that is proton-proton coupling. Then we will study homonuclear 2D NMR. For heteronuclear 2D NMR, we will study the effect of proton or on carbon, or effect of carbon on proton, and in this case we are going to study carbon and proton, both are heteronuclear, and the effect of them on each other. So in that case we use heteronuclear 2D NMR. For homonuclear 2D NMR, the techniques we used is COSY, that is correlation spectroscopy. Correlation spectroscopy. For CO we use correlation, and for spectroscopy S and Y. The second technique we use is TOCSY, that is total correlation spectroscopy. NOESY, that is nuclear Auer-Hazer effect spectroscopy. And ROSY, that is rotating frame Auer-Hazer effect spectroscopy. So these techniques we use for only proton NMR or carbon NMR, and the effect of proton NMR, proton-proton coupling, or carbon-carbon coupling. In heteronuclear 2D NMR, we use techniques which are HSQC, that is heteronuclear single quantum correlation, HMQC, heteronuclear multiple quantum correlation. For heteronuclear, H, M for multiple, Q for quantum, and C for correlation. And HMBC, HMBC stands for heteronuclear multiple bond correlation. So heteronuclear multiple bond correlation. So these are the techniques that can be used during 2D NMR. Here we will discuss how we can study or how we can work with 2D NMR, and secondly then we will discuss COSY technique, that is correlation spectroscopy, in this lecture video. So first of all, how 2D NMR works. During 2D NMR we use RF pulse 1, which is 90 degree or 90x pulse, which causes nuclear excitation 1. And during this nuclear excitation, the nuclei, after spin flipping, they are going to relax, which is denoted with relaxation time T1, and this terminology is also called as evolution. So this is the evolution 1, where the nuclear spin after spin flipping going to relax, and they produce sinusoidal curve, which we studied in our previous videos. So you can watch my previous video for this nuclear excitation or RF pulse and then spin relaxation. During this spin relaxation, there may be magnetization transfer for the protons or the carbon, which are coupled to each other. And after this magnetization transfer, we use another RF pulse, which is also 90 degree X pulse or 90x pulse, which causes nuclear excitation 2. So this is the second excitation. So that is the reason that we call it 2D NMR, because we use RF pulse 2 times. First RF pulse, and after relaxation second RF pulse is applied, and then we give a time for relaxation of these nuclear excited atoms, and this is called relaxation time 2 or evolution 2. After this, we get our data in the FID form, that is free induction decay, and this is called data acquisition. So free induction decay is also discussed in our previous lecture, so you can watch on my videos. Here we are going to discuss some more details on this. When RF1 pulse is applied, there will be excitation of the, let's suppose, proton A, and after evolution we get sinusoidal curve, and this will provide us frequency 1, which is equal to cos omega A for this proton, and T1 is the time for evolution. When RF pulse 2 is applied, let's suppose it causes excitation of the proton B, and it after evolution time or relaxation time T2, it will give us frequency 2, which is cos omega B T2. And after this RF pulse 2, this cycle repeats again and again. So we will give the nuclei, we will provide time to the nuclei to get equilibration, to get equilibrated or preparation. So this time is called equilibration or preparation time, and after this again RF1 pulse is applied, and then RF pulse 2 is applied, and this cycle repeats again and again, and it will enhance our signals. So this repetition is only to enhance the signal, and in this case we get, after some cycles, we get FID, which is the data acquisition, which is called FID or free induction decay. What is equilibration or preparation? We also discussed in our previous lecture that when we apply magnetic field, the protons or the nuclei which are spinning in different states like alpha and beta spin states, they arrange themselves along the magnetic field or against the magnetic field. So this is called equilibration or preparation time. So after this, the FID or free induction decay is the product of frequency 1 and frequency 2. So in this way we get our graph in this form that will give us peaks for which is the product of frequency 1 and frequency 2. So we will get here on this direction we get frequency 1, and on this direction frequency 2, and we get different peaks, which are, some of these are diagonal peaks and some are cross peaks. So these diagonal or cross peaks we are going to discuss in COSY, that is correlation spectroscopy, and then we will discuss it in detail. So during 2D homonuclear COSY NMR, which is also called as correlation spectroscopy, and this COSY technique determines the coupling of different protons. The coupling of the protons which are present in vicinity, or which are coupled with each other, or which are present on the adjacent carbon atoms. During NOESY, nuclear average effect, we study the effect of proton in the surrounding of the proton, which are up to 4 to 5 angstrom distant from each other, but they are not it is not necessary that they are present at the adjacent carbon atoms. But in correlation spectroscopy, the protons should be present at adjacent carbon atom, and it will give us signal, due to which we can find out that these two kind of protons are present at the adjacent carbon atom. So this is the main objective of our COSY spectroscopy or correlation spectroscopy. So in this case, if we have a proton A which is spinning and the magnetization vector is m, during RF 90x pulse, the spin flipping will occur, and it will be on this direction, on let's suppose on z direction or y direction. After RF pulse 1 is applied, And then these nuclear spin will start spin relaxation. So we also discussed that the spin relaxation will be on the 90-degree from this axis. So after the evolution 1, we again provide RF 90x pulse, and let's suppose it causes the spin B flipping spin B towards the same 90-degree x pulse, and it will cause it to orient at the 90-degree. And after this it will also get relaxation. So it will also get relaxation, which is in t2 time. So this is our evolution time 2, in which the second proton will move or will go to the relaxation. So in this way we study the effect of A on B and effect of B on A. So both of these effect will be determined during these two pulses. So it correlates homonuclear chemical shift that are directly coupled together through J coupling. So this correlation spectroscopy correlates homonuclear chemical shift that are directly coupled to each other. So diagonal peaks corresponds to the normal 1D. So we are going to show you that what are the diagonal peaks and cross peaks. So diagonal peaks will represent us the normal 1D NMR, whereas cross peaks represents coupling in the spectrum. So cross peaks in the spectrum will provide us coupling of the proton with each other. So it is used in different coupling protons or coupling carbon atoms. So here we are going to discuss an example where proton A is coupled with proton B and they are present at the adjacent carbon atom, and so it will give us 2D spectrum like this. So here we have 2D spectrum of these two protons which are coupled with each other. So in this case, when we get the signals or frequencies, we get diagonal peaks. These are the diagonal peaks. So we will get diagonal peak for proton A and diagonal peak for proton B, which represents that these protons are present, that is like 1D NMR said that these protons are present in different environment. So A and B, it will give us A peak and the B peak, and which provide us tuplet that A is affecting B and B is affecting A. Then it is further confirmed by the cross peaks. So cross peaks, these are the cross peaks which are not present on the diagonal. They are called as cross peaks. So this cross peak here, if we expand this on the two directions or two dimensions, so it will give us that this cross peak represents that if this peak is present here, it will represent that this proton, which is proton B, is coupled with A. So this is the spectrum of the proton B. So this represents that, let's suppose this is for A and this is for B. So it represents that A is coupled with the B, or this B is coupling with A. And similarly, the if cross peak is present here, then this kind of cross peak will also be present down the diagonal peak, which represents the mirror image of this one. So it will provide mirror image of each other, and it represents that both are coupled with each other. Like here I have written that B is coupled with A. It represents A is coupled with B, then B is coupled with A. So it is not necessary to observe this cross peak, because if this cross peak is present, that it is enough. But this gives us mirror image and of this whole spectrum. So here we have for omega A, and this is for omega B, this is for omega B. So these cross peaks are also called as off diagonal peaks. So in this way, the spectrum will not be the doublet, and it will be different from the 1D NMR, but we will get the signals. And here we are not going to discuss in detail that what kind of peaks will be peak splitting will occur, but this cross peak will represent that B or A is coupling with B, and if this cross peak is present, this also confirm that B is coupled with A, because here we have A peaks for A, so B is coupling with A. Now we are going to take another example. Let's suppose we have a structure like this, CH3, CH2, CH2Cl. So all these protons are different. These are present in different environment. So this is for one carbon proton, second carbon and third carbon protons, and one is coupling with 2 and 2 is coupling with 3, but 3 is not coupling with 1. It is helpful to DNMR when we don't have this structure. If we don't have this structure and we are going to take NMR, then it will be more informative that if one is coupling with 2 or one is coupling with 3, and this it will be more informative. So here we have written that if we don't have structure, then we cannot find out that which proton is coupling with which proton. So that's why 2D NMR is important. So here let's suppose we have the diagonal peaks for 1, 2 and 3 protons. So these are the diagonal peaks, and they represent that 3 different kind of protons are present. And then we get a peak here in the cross peak. So this represents, if we have this peak, it represents that 2 is coupling with 3, or the mirror image of this will be here. So it also represents that 2 is coupling with 3, or here 3 is coupling with 2, 2 is coupling with 3, 3 is coupling with 2. Similarly, we have a peak here, cross peak, which represents that 1 is coupling with 2, and this peak represents that 2 is coupling with 1. So these are the mirror image peaks. So in this way we get the idea that 2 is coupling with 3 and 1 is coupling with 2, but not 1 is coupling with 3. So here we don't have any peak. It means that 1 is not coupling with 3, or 3 is not coupling with 1. So in this way we get correlation spectroscopy, or COSY. So here today we discussed 2D NMR and one kind of technique which is called as correlation spectroscopy. And the NOESY is similar like this, but in NOESY there is no J coupling in the protons. So in NOESY it is long range, or we can say that the protons which are present in vicinity of the proton, when they effect on that proton, so that kind of signal can be produced during NOESY 2D NMR, or which is also called as nuclear Overhauser effect, nuclear Overhauser spectroscopy. So we can, so here we are going to show you that how nuclear Overhauser effect can be effective. So here is a nuclear Overhauser effect. So during nuclear Overhauser effect, the signal of a proton 1H is affected if another proton is close in space, is irradiated or inverted. So here we have this proton and another proton which is not adjacent to this proton, but it is 5 to 6 angstrom distance from this proton. So both will effect on each other. So in this case, like here, if we provide radio frequency or RF pulse and this proton is effecting on this proton, so this will be called as nuclear Overhauser effect. This from CH3 to CH2, this will be J coupling, and it can be expressed by COSY, whereas if this proton is affecting this proton, it can be observed by NOESY, that is nuclear Overhauser effect. This is also called as through space effect. So close in space effect or through space effect. So in this case, during NOESY, the The signals of first proton is affected by another proton during inversion. So this is inversion, that a proton from beta spin state goes to alpha spin state, and it will affect the another proton, and it excites another proton during spin relaxation. So that is the case that after spin relaxation we provide again another RF pulse, and then we observe the effect on each other. So this process can also be observed during 2D NMR, that is called NOESY. So in COSY, the second RF pulse is used to detect coupling effect of proton, whereas in NOESY, second RF pulse is used to detect the effect of proton which are about 5 to 6 angstrom distant from the first proton, that is in space. So this is enough for NMR, 2D NMR, and next time we will discuss mass spectrometry and its different fragmentation techniques and ionization techniques. So thanks for watching my video.